It is my pleasure to be with you today for this presentation about one of today's hottest subjects in astronomy and space technology. The talk was originally presented to a November 2022 gathering of the Grand Rapids Amateur Astronomical Association, but it happened during an unexpected early season snowstorm. So my thanks to John Farish and the staff of the Chaffee Planetarium at the Grand Rapids Public Museum for hosting this archived version for those who may have missed the original and for a wider audience via YouTube. It is really the story of the first decades of the 21st century in science. Probably one of the most significant space efforts, exploration efforts ever. And I think I can present some evidence to support that. But let's start back, way back to 1965. I was attending a meeting of the American Astronomical Society held at the University of Michigan in Ann Arbor. And it was just after Mariner 4 had cruised past the planet Mars and sent some of the first primitive digital images of another world. And prior to that time, Mars was looked at very romantically as perhaps an oasis for life, even higher order life. There were lots and lots of stories about Mars. And yet, this was a scientific breakthrough that showed that the planet was really a desolate desert. And of course, these images are so primitive by today's standards, yet they were cutting edge for the technology at the time. To put it in perspective, the only predecessor to this, I believe, was the Mariner 2 spacecraft to Venus and a couple of probes to the moon. So we were really in the very first stages of planetary exploration. Now, if you go ahead just basically one decade to 1976, that's when the Viking lander showed us these remarkable pictures of a rock-strewn surface. It was when Gerald Ford was president of the United States. And it was also a period when digital technology was really starting to advance. And then throughout almost the entire decade of the 80s, we were sitting back and gaping at some of the amazing pictures coming to us from the Voyager 1 and Voyager 2 spacecraft as they passed by the planets, first Jupiter, Saturn, and then later in the decade, Uranus and Neptune. And Voyager 2 is pretty much our longest surviving spacecraft. It is still transmitting from distances far beyond the realm of the planets. This was all amazing stuff, but it really paled by comparison to the Hubble Space Telescope. Launched in 1990. It's still delivering amazing pictures of deep space objects, some 3 decades later. Throughout the time that the Hubble Space Telescope was doing this remarkable science, there was the realization that it had a limited lifetime, that it wasn't going to last forever. Luckily, there have been service missions that have upgraded the telescope, and in fact, it has survived and had a productive lifetime far longer than was originally anticipated. Hubble is named after a man who was himself a pioneer. Edwin Hubble used the 100-inch telescope, then the largest in the world, out at Mount Wilson in California during the early decades of the 20th century to essentially discover our place in the universe. Keep in mind that that instrument for almost 4 decades was the largest in the world until the Palomar telescope came along in 1948. And that telescope had a mirror approximately 100 inches in diameter, which was only slightly larger than the mirror of the Hubble Space Telescope. With that remarkable instrument, Hubble and other researchers showed that we live in a galaxy, and that far beyond our own galaxy, there are numerous other galaxies. And this is a picture of perhaps the most famous of all the galaxies, one that amateur astronomers are familiar with. Many of you have looked at it in amazement through your telescopes. Not so much because it's impressive looking, but it's very impressive that you are looking back over 2 million years into the past. Now, Hubble's original estimate of the distance of that galaxy was only about half that. How did he come to realize that this was another galaxy of stars far beyond the Milky Way? Well, he observed certain variable stars within the galaxy, stars that were defined by the remarkable Hooker telescope. And notice they had characteristics very similar to well-known stars within the Milky Way galaxy. They essentially became standard candles. And once he had determined that that galaxy was so far away, we came to understand that other hazy blobs in the sky, some of them so much fainter and so much dimmer than the Andromeda galaxy, were themselves other galaxies, basically island universes like the Milky Way and like the Andromeda galaxy, and that they were uncountable. They literally flooded the sky. And the farther we looked with bigger and bigger telescopes in subsequent decades, the more of these galaxies we see. And they're also kind of a time machine, because if the Andromeda galaxy is 2 million light years away, meaning that its light takes 2 million years to get here, then we are seeing that galaxy not as it is today, but as it was 2 million years ago. And the farther we look into space, the more we look into the distant past. So telescopes are, in a sense, like time machines. The bigger the light grasped, the farther we see. That's the impetus for building big telescopes. Let's make sure that we're very clear by what we mean by light time, a light year or a light minute. Let's take a look at our closest stellar neighbor, the sun. Its light takes 8.3 minutes to arrive on Earth, traveling at 186,000 miles per second. A curving beam of light would go around the Earth 7 times in just 1 second. Now, if you did the math, you'd find out that light travels roughly 6 trillion miles in a year. So a light year is a unit of distance equal to about 6 trillion miles. The closest significant star to us in the southern constellation Centaurus is about 4.3 light years away. The familiar North Star, Polaris, 320 light years away. We've mentioned that the Andromeda galaxy is about 2.5 million light years away. Well, we mentioned 2 million. Now it's revised even up higher. Every time we come up with a revised distance for the Andromeda galaxy, we, by extension, come up with a revised distance to the size of the known universe. Our sun orbits around the center of the Milky Way galaxy, about 26,000 light years from the center. And the Hubble Space Telescope, Webb's predecessor, has now looked into the past well over 13 billion years. The universe is indeed a remarkably big place. Here's actually a drawing. Amateur astronomers would understand that sometimes photographs don't do total justice to what you're looking at through an eyepiece. So it's kind of fun sometime to make a drawing. And this is a drawing of a well-known nebula from the Messier list, Messier 16 in the constellation Sagittarius. And it's just a little amorphous cloud nicknamed the Eagle Nebula. And you can see kind of an eagle shape here, the neck and the head, the wings. The features are very subtle. Here's an excellent photograph taken by an unknown amateur astronomer. And in addition to seeing that kind of larger eagle-like structure, we see a little feature here in the middle, a little dark patch. It may not come through too well to you, but it's sort of an eagle within an eagle. It's a dark, obscuring cloud. Well, let's take a look at it through one of the best observatory views, and you see some pretty amazing detail. Within the dark cloud, obscuring dust in the foreground that is preventing us from seeing brighter objects that lie beyond. So it's kind of like a veil. And here, of course, is the famous Pillars of Creation photograph from the Hubble Space Telescope, and how amazingly revealing that is. I don't really have to say a lot more. You're just taking a look at one of the best ground-based pictures versus what the Hubble Space Telescope revealed. They're called the Pillars of Creation because deep inside these clouds, unseen to us in this view, star formation is going on. Matter there is coalescing and eventually will ignite, forming very, very young stars. We sure would like to better understand what is going on behind that veil. And I promise you, this picture is going to come back again a little bit later in this presentation. Well, we could go on and on about the Hubble telescope, revealing pictures of galaxies lying billions of light years away. A wonderful picture here of what's called the Cat's Eye Nebula. It's a planetary nebula. A little bit more about those. They are thought to represent a chapter in the evolution of a star, essentially its last chapter, as it expands to a red giant, or in the case of the most massive stars, to a supergiant. More modest stars like the sun and those of similar brightness and characteristics, as they expand near the end of their life cycles, pulse, and they successively blow off waves of matter that slowly expands into space to form these lovely shell-like features that we call planetary nebulas. Hubble also saw interacting galaxies. Many, many galaxies that were strictly amorphous blobs on Earth-based telescopes became revealed as amazingly complex cities of stars. And I could go on, but then we wouldn't have time to talk about the Webb. Hubble was indeed a remarkable, remarkable step forward in our knowledge of the universe. This picture is on my wall at the office at the Grand Rapids Public Museum, and if I'm kind of in need of a little extra inspiration, I look at it. This is the famous ultra-deep field created about a decade or more ago, when Hubble just sort of stared at a section of sky, I think in the constellation Fornax. There was really nothing there. Maybe a bright star or two, but mostly a black background. But it stared and it stared and it built up energy over a long period of time, and appearing as little blobs, exceedingly faint and reddened for reasons which we'll explain, were uncountable distant galaxies. Furthermore, it has been estimated that those galaxies that are in this frame are over 13 billion light years away, meaning that we are looking that far back into time. Yes, Hubble was a remarkable achievement. I've been around a long time, and I've been into astronomy since I was a teenager way back in the 50s. I've been in it professionally now for almost 60 years. And I have to tell you that even during its first few months, the Webb Space Telescope has impressed me and so many others far more than any of the predecessors. Getting it there was a monumental achievement. But I think the hard work, the effort, yes, the money that went into establishing this platform will turn out to be well worth it. And Webb, and that mistake will happen more than once. Yes, this is the generation of the Webb Space Telescope. Hubble's still around, Hubble's still doing good science. But yes, indeed, this is the age of Webb, which began actually about a year ago now. It doesn't look like any telescope that we previously talked about. Oh yes, it has obviously a reflecting mirror. Even that looks different than any reflecting mirror you're familiar with. And of course, the light is brought to this receptor here, not quite focused, but then sent back down to instruments mounted down in this area here, and also down here. There's one very, very important component that you will not find on any other telescope, and it's this rather interesting looking layered section. It's actually the area of about equivalent to a tennis court, so it's rather large. And it's an incredibly important component. And we'll talk more about some of those various components as we go forward. Now, it was first conceived in the 1990s, called the Next Generation Space Telescope at the time. As the project evolved, it became a joint effort of NASA, the European Space Agency, and the Canadian Space Agency. So there were partners here with NASA as the project evolved. And when approved by Congress in the 1990s, this was budgeted at under $1 billion in 1990 dollars. And it was supposed to be in orbit by about 2007. Well, at least that's what the people who conceived of the telescope told the members of Congress, who had to approve, of course, the budget for this incredibly ambitious project. Now try, if you will, to picture a group of scientists explaining to a group of politicians what this funny-looking contraption is all about and what its potential is. It was quite a sales job. And over the course of the project's evolution, as there were first cost overruns, then delays, then more cost overruns, and more delays still, there were times when Congress threatened to basically put a halt to the project, looking at it as almost one great big boondoggle. But happily, the scientists convinced the politicians that they were far enough along and that challenges and unexpected hurdles were part of the project. They were not unexpected, that they should persevere. And thankfully, they did, and we know where it eventually led. The telescope has to operate under very, very low temperature conditions. And not only budget constraints, but the hostile environment could have doomed the project at any point. The good news is, of course, it was worth the effort. It's named after James Webb, who was an Undersecretary of State for President Harry Truman. He later became the second administrator of NASA, which was formed in 1958 following the Sputnik scare that we all remember. Well, some of us are old enough to remember. And also some of the early failure of America's first effort to put satellites in orbit. It was quite a story of fits and spurts. It put the U.S. space program under an independent agency rather than the military, and that was a good thing. Webb ended up guiding the Mercury, Gemini, and the Apollo programs from about 1961 to 1968. And he also was involved in the certainly some of the more traumatic aspects of the Apollo program, including the Apollo 1 fire that took the life of Grand Rapids astronaut Roger Chaffee in 1967. He's long remembered as a visionary, somebody who really contributed a lot to the success, the overall success of our space program. So it's fitting that the telescope be named after him. It's very interesting to compare the characteristics of Hubble and Webb. Keep in mind, when Hubble was launched in 1990, it was actually using technology that was developed in the 1970s. Just like Webb, it did not happen overnight. It had to be evolved into the instrument that it is today. It had a projected lifetime of about a decade, and here we are, 32 years later, and Hubble is still doing really fine science. Mirror size, 2.4 meters. As noted, approximately the size of the 100-inch telescope at Mount Wilson. Notice the mass, 12,200 kilograms. Pretty heavy. But we had the space shuttle to get it into orbit. Operating temperature, 20 degrees Celsius. Not really a hostile environment. Also, it orbits the Earth, so there would be periods of time when it would be exposed to sunlight, other times when it would be in complete darkness. So there would be extreme temperature changes depending on where it was in its orbit. And then we look at James Webb. Finally got up in 2021. Projected lifetime of 10 years, but there's every reason to believe it will probably last longer because of all the redundancies built into the instrument, and also its remarkable success so far. So we're really on a roll. Let's hope it continues. And you will also notice that the mirror size is approximately 3 times that of Hubble. It is not a solid mirror, but it's a segmented mirror. You would have no way of launching something as heavy as a single piece of glass, and the Hubble mirror was made of glass, into a position not in orbit around the Earth, but far more distant. And we'll get to that in a moment. I think the most remarkable characteristic is the fact that it weighs, despite its huge size, only about half of what Hubble did. And again, the reason for that is that it is not in orbit around the Earth. This gives you a good idea of the comparison between the two instruments. Basically, the Webb telescope mirror is 3 times the diameter, roughly, of Hubble. Gathers about 5 times as much light. 18 segments all fit together like a jigsaw puzzle. Hexagonal sections. And not made of glass, but of a fairly lightweight metal called beryllium, not coated in silver, but coated in gold. A gold plate, a very, very thin layer. The reason is that the Webb is designed to not receive visible light, but rather infrared radiation. Each section weighs about 46 pounds, so a single person could actually pick it up if they were fairly hefty. Quite a remarkable engineering feat to create a reception mirror of this size and yet of a very reasonable weight and mass. Radiation coming to us from space covers a lot of wavelengths known as the electromagnetic spectrum. And Hubble was designed primarily to look into that very narrow region called the visible spectrum. In fact, most research instruments up until well into the 20th century were primarily for visual research. We now have instruments in orbit that allow us to see into the ultraviolet spectrum, X-ray spectrum, even gamma rays. And Webb is designed to be primarily operate at the longer wavelengths in the infrared part of the spectrum. And this is an area that hasn't really been explored too well, and yet it plays a very important role in what Webb is really considered perfect for and was designed for, and that is to explore the early history of the universe. Most of you are familiar with the Doppler effect. It occurs when an object is either moving toward or away from the observer. Consider 2 amateur astronomers on planets greatly removed from one another, and a galaxy is moving toward one of the observers and away from the other. If a spectrum were to be taken of the galaxy, actually light, the combined light of all of the component stars, it would have the characteristic absorption lines that we see in the spectra of stars and are fairly familiar with. Light spread out into component colors crossed by black lines that are signatures of the elements within the stars. This phenomena of wave spreading and compressing due to the object, the Doppler effect, becomes greater the faster the object is moving toward or away from the observer. And very early on in the 20th century, early astronomers such as Hubble and others noticed that there were shifts in the spectral lines of the galaxies, and that the nearby galaxies seemed to have a much lesser shift than those that were more distant, appropriately called a red shift because it tended to go toward the red end of the spectrum. And that's where the expanding universe concept developed, the idea that we are part of this very, very large, slowly expanding cosmos, sort of the raisin bread analogy, that the universe is slowly expanding as the raisins would do within a baking loaf of raisin bread. And regardless of where you are located within that expanding realm of galaxies, as you look out into space, everything appears to be moving away from you. So it's very hard to determine where perhaps the center of that expansion is. But it gave rise to the Big Bang theory that the entire universe is evolving from an event, some kind of a creation event that happened way, way, way back in the past. The problem is that for some of the most distant galaxies, they are reddened so much by the Doppler effect that their radiation is primarily in that infrared part of the spectrum and not the visible light. And that's another reason why Hubble, or whether that's another reason why Webb was built, is to look into that area of the spectrum, the infrared, and to see and detect radiation from very, very distant galaxies. Well, if we're looking at very, very distant galaxies, say on the order of more than 13 billion light years away, we are also looking more than 13 billion years into the past. So Webb is also a time machine. Hubble is orbiting out there at about 570 kilometers above the Earth's surface. But Webb will be sent out to a distance 4 times as far away as the moon. That was the problem that the designers faced. This telescope could not be located in Earth orbit. It needed to go someplace where it was very, very dark and very, very cold. In order to explore that infrared spectrum efficiently, this telescope has to operate at a very, very low temperature of less than 200 degrees or minus 200 degrees Celsius. In fact, rather close to what we would term absolute zero of minus 273 Celsius. And one of the few places where that could happen is out at a very interesting point called the Lagrange point. Now, I'm not going to get into a big discussion of gravity and the various forces operating here. That's for another subject. But what I would like to explain to you is that this telescope basically hovers at a semi-stationary point in a manner that the Earth is between the telescope and the sun. Now, the Earth is not going to occult the sun. It's not nearly big enough to do that, but at least the lighted side of the Earth is away from the pointing away from the telescope. That's advantageous in maintaining the conditions required. And secondly, the telescope is at a greater distance away from the planet Earth than Hubble was. And therein lies one of the reasons why this telescope had to be built with so much care and precision, why it had to be tested again and again and again. The reason being that, unlike Hubble, which could be serviced by the space shuttle, there is no way that we're going to be able to send any kind of repair mission out to a distance 4 times that of the moon. So it is incredibly important that this telescope be designed right the first time. Unlike Hubble, which you may recall had a glaring flaw when it first started to image stars. As incredulous as it may seem today, the instrument was not configured properly. Luckily, repair missions were sent out, first to give it some corrective optics and later to provide some electronic updates that kept the telescope operating for over 3 decades. We have no such option with Webb. Therefore, it had to be tested, retested. Redundancy after redundancy had to be built into this. And all of that required additional time and additional money. And that's one reason why there were so many delays and why it ended up, excuse me, taking close to $10 billion to complete. The launch date got set back again and again. Hundreds of people, from scientists to engineers and technology experts, were involved in what is now a quarter-century project. That's right. Almost 25 years. This is a mock-up that we see in this photo on the lawn, I believe, of the Houston Johnson Space Center in Houston. You get an idea of how big the telescope is, how important that layered contraption there that protects the telescope from the intense radiation of the sun. Gives you an idea of how big that is. And this all had to be carefully folded up and launched out to a distance 4 times that of the moon. I think to say that it's the most complex scientific instrument ever conceived and built by humans would be somewhat of an understatement. So much had to be designed in theory and then actually produced. The segmented mirrors, very, very precise controls that had to be used to keep them aligned, each one individually aligned with the others. And then it all had to be mounted, folded, and stowed away aboard the giant rocket that would send it into space, contained within the nose cone area, and here we see a mock-up of the nose cones in the rocket. And this is the actual Webb Space Telescope itself folded up prior to its launch. Happily, it was launched by a highly reliable rocket used over and over again by the European Space Agency from their launch facility in French Guiana in South America. And as you know, it all happened on Christmas Day last year. So we're at this point coming up on about 1 year already that the telescope has been aloft. As it was climbing toward that L2 point, the instrument was unfolding, and as it approached its residency there, it also was unfurling. Now, all of this had to be done by remote control. And again, there were hundreds of things that could have gone wrong. So many intricate commands, so many operations that had been pre-programmed and sequenced in such a way that you could not make last-minute and on-the-fly adjustments. Notice the fragility of that heat shield. And that's basically what it's doing. It keeps the telescope itself very, very cold, while some of the instruments mounted on the opposite side of that heat shield are kept warm. Once unfolded, it was time for alignment and calibration, and that went on through pretty much March and into April. And all of the mirrors had to be carefully aligned with one another, all again by remote control, one by one, to get the light being reflected by these multiple mirrors to come to a single receptacle, what we call the secondary mirror, and then sent down to its final focus into the instrumentation, which is hidden here underneath the telescope mirror. Time does not permit us to get involved with all of the different instruments, but they are really, really varied, and I'm going to talk a little bit about them as we explain what each is designed to do. The original images were pretty fuzzy, and that was expected. There was nothing surprisingly about that because the mirrors all had to be brought into alignment. But once that alignment happened, we got a perfectly focused image of an unknown star here. And if you were to look very, very, very carefully in the background, you would see some reddened objects, which are not stars, but already very distant galaxies showing up. Well, this is where things were in early April, and at the end of the program here, we're going to show you some of the latest images that started emerging beginning on July 12th. There are a number of things that Webb is designed to do, enhancing, in some cases, previous programs, and in other cases, breaking exciting new ground. The big one, of course, is looking back in time. Because of the capability to see into the infrared spectrum, we're going to be able to see extraordinarily weak radiation emitted by the youngest of the galaxies. So it's basically look-back time that's so important. And as we're going to see here in a moment, it also can penetrate. It can see through the dust and some of the obscuring material that prevents us from seeing things that lie beyond, such as perhaps the black hole lurking at the center of the Milky Way galaxy, long speculated. Could we actually see evidence of that black hole more vividly than we do now? It will study the life cycles of stars, and I'll have a little bit more to say about that, looking at both the earliest stages as stars are born out of clouds of gas and dust, and their final stages as they die while producing a planetary nebula. And we'll also look at the many, many planetary systems that are known to exist. Planetary systems that we didn't know anything about prior to 1995, in which we now have discovered something like 2,000 other exoplanets orbiting around other stars, and the number just keeps growing. we know that planets around stars are pretty much the rule rather than the exception. And we'll actually be able to study the atmospheres of some of those incredibly distant stars, even though we don't see the planet itself. Through spectrographic analysis, a very, very, very sensitive spectrometer system aboard Webb will allow us to understand these characteristics of stars far, far too distant to, or rather planets that are far, far too distant and too close to their parent stars to actually image directly. Webb had sort of a survey telescope predecessor in the form of the Kepler spacecraft. And that was one of the more productive spacecraft during the second decade of the 20th century. And it stared at a number of stars in a small area of the sky, looking for the telltale sign of planets, namely a slight dipping in the light output of a star caused by a planet transiting in front of it. Now, it's only by happenstance that you catch a planet transiting in front of a star. Its orbit has to be oriented such that that can happen, and that you have an instrument sensitive enough to measure that slight drop in brightness. But Kepler was really, really a workhorse, and it did come up with a lot of suspects of planetary systems to be further explored by telescopes with greater capabilities. And of course, the one with the greatest capability is the one we're talking about. Webb will help us better understand not only how many planets are out there, but it will have that capability, as I just mentioned, to actually analyze some of the characteristics within the atmospheres of these planets. This is not an actual photograph, it's more like an artist's conception. Well, it is an artist's conception. And it is of another planet, an exoplanet orbiting some anonymous star. And it's a planet with an atmosphere like that of the Earth. Well, it has an atmosphere, maybe it's Earth size, similar to Earth in some ways. But does it also harbor life? That's a big stretch. But maybe Webb, with its remarkable spectral characteristics, will be able to find the signatures of water vapor, oxygen, carbon dioxide, and nitrogen. If these elements and compounds exist within an atmosphere, it certainly supports the idea that life is conceivable. It will undoubtedly also expand that inventory of known exoplanets in a big way. We've long had a pretty good idea of how stars evolve, beginning as dark spheres within nebulous clouds, slowly contracting under gravity, igniting as stars, and then going through an evolutionary process. Eventually to die, at least for stars like the sun, as a planetary nebula, with the central star collapsing to a white dwarf. It's a pretty straightforward picture. There's lots of details to be filled in. And once again, it's Webb that is called upon to give us the details. Because you see, it can pull back the veil of dust that blocks our view of so much of the universe. Here we are once again with the Hubble Space Telescope picture of the well-known pillars of creation within the nebula M16. And that was just a really, really mind-blowing picture for a long, long time. It found its way into the popular media. It was representative of one of the most impressive achievements of the Hubble among its many impressive achievements. And yet there is stuff going on within that dark area that scientists are just so anxious to learn more about, because we think this is kind of like a cocoon, and that star formation is going on deep down inside, if our current theories are correct. That is why this photograph, made by Webb, one of the first to be released, is so incredibly revealing. Now, I couldn't orient them exactly the same, so you can see the scale on this one's a little bigger, but you can see the basic features in both, and you can see how much more detail there is. I certainly call your attention to this area right in here, which would coincide roughly to this area, I believe, right here. You can see through it some, but look at what you can see when you look at the picture on the right. So much more detail. And you can see star formation occurring, like right here. These stars are there in this picture. They're just hidden from view by the foreground dust. We are seeing into the cocoon. We are finding out what is going on. These are very young, hot stars in the very earliest stages of their lives. It gets better. This is a region of a dark nebula around the star Eta Carini in the southern hemisphere. We can't see it from here. But what has happened is that very hot young stars in here, previously unseen until Webb pulled the veil, is pushing this material outward due to radiation pressure. And we get this wonderful hedgerow effect. This is one of the pictures that impressed one of the principal investigators that's from here in Michigan the most, because it gives a very clear idea of what could be going on deep inside a nebula as young stars are forming. This is a fine picture of the Orion Nebula. It's actually taken by one of our best astrophotographers here in the West Michigan area, Joe McBride. And we marvel at how detailed that is. Well, here's a comparative picture of a section of the Orion Nebula, generally this section right in here, taken with the Webb. In fact, I think this star right here coincides to this one right there. Look at all the amazing detail. It's almost like you're zooming in to this stellar nursery that we long knew existed within the Orion Nebula. It's just a perfect breeding ground for the formation of stars. And what Webb has found is just an amazing number of features previously unseen that will keep astronomers and other researchers scratching their heads and pondering for quite some time. How do all of these varied features fit into the overall picture of how stars evolve through their existence? Webb is in the first stages of doing exactly what it was planned to do, and that is to fill in a lot of the unknowns within these pictures of how stars evolve and eventually die. We mentioned the later stages of evolution, producing a planetary nebula. I was fortunate to get into the southern hemisphere in 2019 and to see so many of the wonders down there that I'd never seen before. Kind of a bucket list trip. And we had access to a 20-inch Dobsonian telescope, so it was quite a feast of visual observing. And among the intriguing objects was what's called the Southern Ring Nebula. Looks somewhat like our Northern Ring. In fact, when you take a picture of it, or when Hubble took a picture of it, it does. It looks a lot like the classic picture of the Ring Nebula in the constellation Lyra that many of the amateur astronomers are familiar with. When Webb took a look, it got us deeper into the heart of the nebula. The central star, which is evolving into a white dwarf, is much more prominent, as are the filamentary structures within the expanding shell. It also took a look at some other planetary nebulas and got similar results, but we need to hasten along. As I indicated earlier, the prime subjects for Webb are galaxies. Because when we look at these largest structures in the universe, we're actually looking ever more deeply into space, as a point I've made a couple of times here today. This particular galaxy is M74. It's in the constellation of Pisces, visible in the northern hemisphere. And its profile is pretty much face-on, so that you can see the arms of the galaxy, but in such amazing detail here in the Webb picture, where we see the bright nebulous areas, and we are looking past a lot of other features of the galaxy that tend to distract from what astronomers would love to know, the dynamics that are going on, not only within the individual features in the arms of the galaxies, but deep down in its core. And there could be a black hole here. We don't know for sure. We do know, of course, that there is a black hole at the center of the Milky Way galaxy, and an analogy here would be very interesting. The galaxy is about 32 million light years away, and that's why it becomes a subject that we can study in some detail. And you'll be hearing more about that in other galaxies. Webb has also shown a group of stars called, a group of galaxies, excuse me, which is called Stephan's Quintet. And Stephan's Quintet is in the constellation Pegasus, I believe, in the northern hemisphere. Galaxies interacting with one another. This is a Hubble view here on the left, and over on the right, we see a much more revealing view taken with the Webb Space Telescope. Once again, allowing us to sort of pierce into the galaxy and to see details far more vividly than with any predecessor. Let's end by looking at Webb's first effort at a deep sky field. Bill Nelson, the NASA administrator, noted at a press conference that the amount of sky that we're looking at here in this, covered by this image, would be the area covered by a grain of sand held at arm's length. So if you were to hold a grain of sand out at arm's length, the angular amount of sky covered is about analogous to this photo. We are looking at a foreground cluster of galaxies. I think these are about 250 million light years away. They're the galaxies that look larger and less red. This, of course, is a star right here in the foreground. But look at what lies beyond. Look at these reddened objects, which would have been totally invisible in Hubble, but are clearly revealed because of the reddened and infrared radiation coming to us from them. Way, way, way out there in space, perhaps as far away as 13.6 13.6 or 13.7 billion light years. We could be looking back at an epoch in the history of the universe only about 250 million years after the Big Bang itself. And to put all of that into perspective, one more thing I want to mention before we move on is that there's kind of a gravitational lensing involved here. The foreground galaxies exert gravity on the light from the distant galaxies in the background is actually affected by the gravitational attraction of the foreground galaxies, and it causes sort of a distortion, a gravitational lensing effect it is called, which actually allows us to see these galaxies more clearly than we would in the absence of this lensing effect produced by the foreground cluster. It's quite astounding indeed. In summary, back in say around 1990 when the Hubble Space Telescope came online, one of the largest telescopes in the world at the time, the venerable 200-inch telescope at Mount Palomar, could look at the universe as it was approximately 6 billion years after its formation. By 1995, when the first of the Hubble deep fields came along, we were able to see out still further to a period maybe about 1.5 billion years after the Big Bang. That view got extended still further with successive ultra deep field views by Hubble, until we were out looking back in time maybe as much as 3.5 billion years. That in itself is remarkable. The general consensus at present, always subject to possible change, is that the universe is perhaps 13.8 billion years old. Certainly less than 14 billion years ago. Now, these are big numbers. They're extraordinarily hard for anybody, even if they've been studying the subject their whole life, to fully comprehend. I certainly can't get my head around it completely, so I don't expect you to. But you are looking so far back. And could you be looking ever closer to the beginning? Perhaps. We think Webb has the capability to take us back to look at the universe as it was only about 200 million years after its formation. In other words, right in its infancy. And therefore give us a better idea of the origin of that universe. Did it begin with a Big Bang? It may have begun in complete darkness before the formation of any stars. Forces that would create a cataclysmic event that would basically ignite the universe and cause it to glow and to form stars within great cities of stars called galaxies. Webb, in the coming decades, hopefully within the next 15 to 20 years of its useful lifetime, will look into that earliest episode of the universe. That was one of the most important things it was designed to do. And if it continues to perform as well as it has so far, those of you who will be following its progress intently in coming years are likely to see even more revelations than we already have. Also, we may get closer to the time when we will solve or at least have a better idea of whether we are the only intelligent beings in this universe. There's probably a good chance we are not the only living organisms. Somewhere out there, amongst all of those planets, circling all of those stars, there have got to be planets with organic materials. In fact, there's already strong evidence for that. But did the processes occurring on the surfaces of these bodies allow for the formation of intelligent beings? We may never know that answer to that question, but then again, maybe one day we will. And Webb may help us to that discovery. Who knows? I'm really envious of the coming generation of scientists. Keep in mind that some of the people that worked on this project spent their entire careers getting the telescope into orbit. And so now it's a younger generation of scientists who are going to profit from the efforts of their predecessors and who are going to use the intellectual and technical tools at their disposal to take our knowledge of our cosmic environment to the next level. That's, to me, is really, really exciting stuff. Thank you very much for your attention. If you wish to get in touch with me, you're welcome to do so. Contact information is here. It's been my pleasure to present to you this survey of the Webb Space Telescope, and basically to share with you my incredible enthusiasm for its potential. Thank you.